welcome back. So let's do one example, a live example of how this incremental equivalent stuff is useful to us, right? So what is the most common nonlinear element that you are familiar with? I'm sure the first nonlinear element that we have encountered in previous courses is a diode, is a PN junction diode, right? So let's replace our nonlinear element with a PN junction diode. This R is equal to 1 kilo ohm. Let's say this voltage is 1 volt, right? And I know the current voltage relationship of a diode. What is the current voltage relationship of a diode? If I sketch, if you say this is a diode, the voltage across the diode is Vd, and let's say the current through it is Id, right? What is the typical current voltage relationship of a diode? It goes like exponentially when it's forward biased, right? And it goes something like this when this is reverse biased. Now this has to go through 0, which I am struggling to draw. So this is not to scale. So this is, let's say, Is. And what is the current voltage relationship? Typically we express it in this form. Id is some Is exponential Vd over Vt minus 1, where Vt is approximately equal to 25 millivolt at 300 Kelvin. Again, this is not exactly 25 millivolt. We make our life easy by making it 25 millivolt. It's 26 millivolt, closer to 26 millivolt than 25, but 25 is a very friendly number, so let's go with that. Okay, so now as you can clearly see, this is a nonlinear equation, right? So we need to figure out the currents and the voltages, right, across and through this diode or in this network. So essentially what we are saying is, if I know this, how do I figure out this current I? And for that you will have to resort to some graphical method, right? And you can write down the equations. What will you do? How will you go about writing it? So we know that Id Vd characteristics is this. So essentially I is common. So what will you do? We will write the current through the diode, right, is I, which is equal to Is exponential Vd over Vt minus 1. This is equation 1. And what is the other equation? The other equation is this current is also the current through the resistor, and that is nothing but 1 minus Vd by 1k, correct? So now this is equation 1, this is equation 2, correct? You can solve them use a numerical analysis, or you can say that I will sketch the on the IDVD characteristics of the diode. I'll also sketch the current through the resistor. Let's say the current through the resistor goes like this, correct? So let's say this is 1 minus Vd over 1k, and I will plot it, and I will find out where these two plots intersect, right? And I will say that this is my actual solution. Let's say this is VDQ, this is IDQ, where Q refers to the quiescent currents and voltages. right? Okay, so I can do all these things, and let's say I have done that. Let's say I have done that, and I have found that, right? So let's assume VDQ is approximately equal to 0.7 volts, right? This is an approximation that we generally take in case of a diode that is we say if the diode is on, right? Depending upon the type of diode, let's say it's a silicon diode, and if we have certain ranges of currents, we say that the on voltage is 0.7 volts. But note that this concept of on voltage does not anyway mean that if the diode is on, the value of VDQ is 0.7 volts. It doesn't mean that. It's an approximation that holds for certain ranges of currents, right? If the ranges of currents changes, let's say, so for example, in this case, if VD Q equal to 0.7 volts, what is the current? I is equal to 1 minus 0.7 by 1K, that is 0.3 milliamps. Okay, so as you will see that if you plug in these numbers, right? If you plug in these numbers into the diode equations, you will see that it will not be an exact match, but it will be a ballpark match. However, if you now say that however, if I now say that the resistance is, instead of 1K, is like 10 ohms, right? If the resistance is 10 ohms, then if I use the same equation, this current will suddenly jump to like 30 milliamps, right? So if it jumps to 30 milliamps, then obviously your VDQ value will not be 0.7 volts. It will be something different, and that will be governed by the IDVD characteristics of the diode. So as it turns out, for a certain ranges of current, these 0.7 volts, 0.65 volts values that we generally take hold true to some extent, but it's not ubiquitously true. For this course, we'll assume that since we will be operating under current ranges of a milliamp or so, we will again say that let's assume VDQ to be equal to 0.7 volts, right? But you should always keep it at the back of your mind that it's not as if there is this concept of cutting voltage that suddenly before 0.7 volts a diode diode is off, and after 0.7 volts a diode is off. Diode starts to contact, because clearly your IDVD characteristics doesn't point to that. Okay, so this is an approximation that we take. Fine. If my quiescent voltages and currents are these, what is the next step? Now if I tell you that I want to know what is the total current if my input is, let's say, 1.1 volt, and I have used the same diode, same resistance, and so on, right? So I want to know, let's say, V0. Okay, so what should I do? Note that I already have the information of what was the case when VDQ was 1 volt, or rather VDQ was 0.7 volts, right? When input was 1 volt, let's say this is equal to 0.7 and IDQ is 0.3 milli, right? So let's say that's how the graphs are, right? I just pulled something out of the head. Now what I am asking is that I want to find out a different solution for for the case of when input is 1.1, right? So essentially what am I asking? I am asking is that if the input changes to 1.1, I know that this curve will shift, right? So essentially now what we are asking what is this new point, right? New current point. So one option will be, let's plug in these values again, express this graphically. But now we know that we need not do that, correct? Why? Because I know I can replace, I already have the values for 1 volt, right? We already have the values for 1 volt input. All we need is the values for 1.1 volt input. So right, so what am I saying? What am I saying? I already have a value for 1 volt input. I need to find out what is the value for 0.1 volt input, correct? So essentially what am I saying? I am saying I already had this battery of 1 volt. What am I doing? I am applying another increment on top of it of 0.1 volt. I knew that I had a quiescent current of 0.3 milliamps, right? I am trying to figure out what is the new quiescent current is, or let me simply call this delta I, right? So this is the current, and I knew that the voltage across the resistor was, in case of 1 volt, was how much? Voltage across the resistor, so this was 0.7, so the voltage across the resistor was 0.3. This voltage across the resistors was 0.3 volt. But I am asking what is the extra delta V, right? What is the extra delta VR, right? Voltage across the resistor, right? We know the condition under the black inputs. We now need to know the conditions under the orange inputs, and for that what we need to do? We need to sketch the incremental equivalent, right? So what is the incremental equivalent? We replace all the elements with the incremental equivalent, right? So what is, let's start from the left. What is the incremental equivalent of the DC 1 volt? The incremental equivalent of DC 1 volt DC battery is a short circuit, correct? What will you do with the incremental input? This is the delta V. This is the incremental input. We have to retain the incremental input, right? So this retains as 0.1 volt. What will you do with the diode? We have to replace the diode with some nonlinear, some linearized version of it, right? We'll have to quickly figure out what is the linearized version of the diode, and we have to replace the resistor with this linear incremental equivalent, which is a resistor of same value, right? So this is 1K. So now what is the missing piece? The missing piece is what is the incremental equivalent of the diode, right? So in a forward bias diode, right, ID is Is e to the power Vd over Vt minus 1, right? So if Vd is greater than Vt by a factor of more than 3, let's say, I can simply neglect the minus 1 term, and I can say that ID is equal to Is e to the power Vd over Vt, correct? Okay, this basically eases our life, right? And we have already figured that Vd is 0.7 volt and Vt is 25 millivolts, so the ratio is quite more than 1, so we can safely neglect that. So which essentially means that this is the ID-Vd characteristics of the diode. So what is So this is my f of v, right? So what is del f del v? For certain quiescent point VDQ, this is nothing but del ID del VD around an operating point of VDQ, right, which is nothing but, in this case, IS by VT e to the power VD over VT, which is nothing but ID Q by VT, correct? So this is evaluated at VDQ. Since this is evaluated at VDQ, I get del F del V to be IDQ by VT, right? So now, so what is this element? What is this element? This element is nothing but 1 over del F del V evaluated at VDQ, which is nothing but VT over IDQ, correct? So what is this? What is the unit? What is the unit of this VT over IDQ? We did del I del V, right? Del I del V is conductance, 1 over del I del V is the resistance. So essentially the diode, a forward bias diode, gets replaced with a resistance, right? With a small signal resistance, right? With a small signal resistance, let's call it RD, whose value is equal to VT over IDQ, correct? One important thing to note here is that the value of the small signal resistance depends on the quiescent current, right? The value of the small signal resistance depends on the quiescent current, and that makes sense. It's a nonlinear device. Since it's a nonlinear device, it makes sense that its derivatives can depend on where in the IDVD characteristics you are taking the derivatives, right? If it's independent of wherever you are taking the derivatives, then it's very likely that the stuff is fully linear, okay? So now what are we after? We are after delta VR, and what will be delta VR? So this will be our delta VR. So what is delta VR? So let me be consistent and use the same orange color. So delta VR will be 0.1 times 1K divided by 1K plus VT over IDQ, or simply I can as well evaluate the value of VT over IDQ and replace, right? So what is VT over IDQ? So this value is so let me go to the next page. So RD is VT over IDQ, which is 25 millivolt divided by, what was IDQ? It was 0.3 milliamps. So this is approximately, right, 8 ohms, 8.33 ohms. So let's say it's 8 ohms, correct? So which means what is delta VR? So now my delta VR is nothing but 0.1 times 1K by 1008 ohms, 1 kilo ohms, or let me simply replace it by 1000 ohms, correct? So whatever be that value might be, this is that value, okay? So what is the total voltage? The total voltage total voltage across R is equal to quiescent, right? So VRQ, that is the quiescent, plus delta VR. What was VRQ? It was 0.3 volt. And what is delta VR? This is 0.1 times 1000 by 1008, right? So this will be your total voltage across the resistor. Similarly, you can also find the total current through this loop. So what will be the incremental current through this loop? This incremental current, that is delta IR, is 0.1 volt by RD plus R, which is 0.1 by 1008, right, amps. And you already knew the original current, original I, right? So you simply add up this delta IR to the quiescent I. So your total I will be IRQ plus delta IR. Okay.